Okay.
So, our next speaker is Siran Lee from Rice University, and he will talk about the isometric immersion problem.
Yes. So yeah, thank you very much. I'm Siran Lee. So yeah, I'll talk about the classical isometric immersion problem. So yeah, it's a revisit. So basically, I'll summarize various different ideas or different approaches towards this problem, and I'll emphasize three probably less known methods, which hopefully give some new which could yield certain new results in this field. So yeah, before I start, I would thank Armin very much. Thank you for the invitation. So the isometric immersions problem is one of the very classical problem in differential geometry or geometric analysis and also nonlinear PDE. So the setup of this problem, which is a purely geometrical one, is rather simple. So suppose I start with a Riemannian manifold or a pseudo-Riemannian manifold, sigma g, and an ambient manifold n g bar, such that the dimension of sigma is less than the dimension of n. So the question is, does there exist an isometric immersion or an isometric embedding from sigma into n? Okay, so yeah, of course, for isometric immersions, we can ask various other problems like stability or uniqueness. But here in this general formulation, let me first emphasize the existence aspect. So yeah, by an isometry, it means that the embedding or the immersion pull back the ambient metric G bar to G. So in other words, if X and Y, there are two vector fields on the domain manifold sigma, then G bar, the inner product from the metric G bar acting on df of X and df of Y, so that's the push forward of X and Y via the map F. So that equals to G at XY. So for every point, in the classical setting, this is the condition of isometry. And by an immersion, it means the differential, exterior differential of F. So this is injective. And by embedding, it means that furthermore, the map F is also injective. So this is a rather simply formulated problem. So why do we care? So why do you want to study the existence of isometric immersions? So there are different aspects of motivations towards this problem. So I'll mention three. So from the differential geometric point of view, so if I take the ambient manifold to be Rn delta, so delta is the Euclidean metric. So if the ambient space is Euclidean, and then if we can prove the existence of isometric immersions or embeddings, so it actually means that every Riemannian manifold, although it's defined intrinsically, they're not very mysterious. Right? They can be viewed as immersed or embedded, respectively, Euclidean submanifolds. So this is indeed the original motivation of the legendary mathematician John Nash in his works in 1954 and 56. So this is the geometrical aspect of the motivation, and also physically, the definition of quasi-local mass in the study of mathematical relativity is closely related to the problem of isometrically embed or immerse a two-sphere with various curvature conditions into an ambient three manifold. So for example, we have the ADM mass by Arnold, Desser, and Misner, and also Shin Yao proved the quasi-local mass, positivity of quasi-local mass, and also there are other variants of masses. So for example, the ones proposed by Melissa Liu and Shintong Yao, and also Mutao Wang and Shintong Yao, and many others. So this is the physical or general relativity aspect of the motivation for the isometric immersions. And also from the analysis per se, it is a rather challenging nonlinear PDE problem. And yeah, also the study of isometric immersions gives rise to various novel tools, give rise to various novel tools in the study of nonlinear PDEs. So for example, we have the hard implicit function theorem by Nash, or the so-called Nash-Moser iteration. And these, the 1956 Nash isometric embedding paper for CK embedding k greater than or equal to 3. And also, from Nash's 54 paper for C1 isometric embedding, it was later developed by Gromov into his book partial differential relations, and these epitomizes in the so-called H principle, which is rather well known today. And also, for example, in Nirenberg's PhD thesis, he studied the classical Weyl problem of isometrically immersed S2 with positive Gauss curvature into R3. And this leads to his theory of fully nonlinear second-order elliptic equations of the Monge-Ampère type. And also the Russian school approach towards the isometric immersion has relations with Alexandrov geometry, etc., etc. So we mentioned various motivations for this problem. So I'll mention also summarize briefly the history of several aspects of the problem. So let's first focus on the Weyl problem, so which was proposed by Hermann Weyl in 1916. So the problem is very classical. So if sigma is a topological two-sphere and equipped with a metric G with positive curvature on sigma, so does there exist an isometric immersion into R3? So Weyl himself approached this problem that raised by him, and actually he I think he achieved various a priori estimates for this problem. And in 1938, Hans Louet he proved he proved the existence of isometric immersions for analytic metric G, where the Gauss curvature is strictly positive. And in 53, Nirenberg proved that for G being C4 with a strictly positive Gauss curvature, and there exists the isometric embedding. And in 62, Heinz relaxed the regularity condition in Nirenberg's paper from C4 to C3. And in much later, 30 years later, Pengfei Guan and Yanyan Li, and also Jiaxin Hong and Claude Zuili, they proved in different papers the Nirenberg's result, but with a K possibly degenerate. So it's just greater than or equal to 0. So this is done by a smoothing in the conformal class, and by sharpen actually Nirenberg or Weyl's a priori estimates, which in turn doesn't depend on 1 over K. So in this setting, they can prove the existence of a C11 isometric immersions, or embeddings. And in a recent work, Siran Lu proved a much sharper result. So G only has to possess 2 derivatives, with the second order derivatives being Dini continuous. And for this, we also require that K of G is strictly greater than 0. So these are the positive or affirmative results for the Weyl problem. And there is one negative result for the degenerate case. So in 1992, Aya and Brago-Scheffel, using different methods, they produced a metric which is real analytic and has Gauss curvature strictly, sorry, this is a typo. So Gauss curvature strictly, no, it's correct. So it's strictly positive everywhere and degenerate at only one point. But yeah, they proved that this thing actually has, well, by Guan Li's result, C11 isometric embedding, but it does not have C21 isometric embedding. So the regularity for the embedding is not automatic. So yeah, this is a history for the Weyl problem. So yeah, let me mention another few related problems. So yeah, we talk about the results by Nash. So for C1 and CK isometric embeddings and immersions. So yeah, this is a existence, or yeah, these are the existence theorems in the large, in the sense that given any metric G, which has no particular curvature condition, so you can prove there exist isometric embeddings or immersions into Rn for n large enough. So if you have a high enough codimension, then you can always do the existence. So yeah, as we mentioned, the C1 isometric embedding work by Nash leads to the Gromov's H principle, or in other words, the convex integrations. And recently, pioneered by the Lelis and Sekihide, is connected to fluid dynamics, to the production of wild solutions for Euler and Navier-Stokes equations. So these are the works by Nash. And also there are several non-existence results. So yeah, in the sense that if you have a metric M, a metric G on the surface, and usually, yeah, by assuming the negative curvature, and then it is known that under certain regularity conditions, it cannot be isometrically embedded into R3. Yeah, so for example, the classical result by Hilbert and Coulomb-Boson, they proved that the pseudosphere, which also appeared in Andy's talk, so the pseudosphere of Gauss curvature constant -1 cannot be embedded into R3 via a C2 isometric embedding. And there are various results sharpening these assumptions. For example, by requiring the suitable decay rate at infinity. So yeah, we mentioned the work in 1993 by Jiaxin Hong, and also Cao Huang Wang. So this is Hua Wang, and yeah, he's in the audience, in 2016. So non-existence results. So on the other hand, there are certain rigidity and uniqueness results. So for the Russian school, the Alexandrov geometry group, so they actually proved that the convex polyhedra have certain kind of uniqueness. So here convexity is the crucial word. So usually by having the same Gauss curvature, you can have two versions of the polyhedra, one convex and one concave. So if you require convexity, and then you, in many cases, you have uniqueness. And we also mentioned Pengfei Guan and Shen in 2015. They proved certain rigidity results with the ambient space not only being R3, but it can be space forms. So simply connected manifolds with constant curvature. So this is proved using an earlier result by S.S. Chern. So Chern has a uniqueness and rigidity results based on the Garding inequality. So it's the crucial ingredient is also to explore the convexity. So Guan and Shen, they proved the rigidity in this case, and also for a recent work by Chunhe Li and Pengzi Miao and Zhizhang Wang, so they proved certain rigidity results for the so-called extrinsic scalar curvature. So it's also called the sigma-2 curvature for isometric embeddings of two spheres, the Weyl problem, but into a warped product space. So that's the rigidity and uniqueness. And also, as we know, the existence of isometric immersions, they are, well, from the PDE point of view, they can be summarized as the Gauss, Codazzi, and Ricci equations. So these are the compatibility equations on the level of curvature for isometric immersions. So for the mathematical elasticity group, for example, by Philippe Cialet and Christine Nell and Sorin Madare, so they proved under various low regularity conditions for the second fundamental form, they relate the Gauss-Codazzi-Ricci equations to, well, there are actually also sufficient conditions for the existence of isometric immersions. And also, Chen's, Lamrod, and Wang, they use a fluid mechanical formulation. And also recently, Florian Littinger, talk about the optimal regularity case for isometric embedding of a surface into R3. So for the Gauss-Codazzi-Ricci equations. Yeah. So I briefly summarized the history of this problem and several related aspects. So the methods is also manifold. So there are multiple approaches to this problem, and each, historically, each person basically look at this problem from different aspects, and they yield, they give rise to different results, by using different tools. So for example, they're also subject to different curvature assumptions and regularity assumptions. So I mentioned several approaches. So mostly PDE approaches. So for example, the original work by Heinz, and also in a short, less known paper, but very brilliant one by Fanghua Lin. So they analyzed this problem by the Darboux system. So it's a second order 2x2 elliptic system, fully nonlinear. So Darboux system, if you write the second fundamental form, view it as a metric on the domain manifold, and write it in isothermal coordinates, and in the case that the target manifold has constant curvature, and actually it looks like the prescribed mean curvature problem studied by Wenter. So this is the Darboux system, and also it can be formulated as a nonlinear Mogent pair problem by looking at the so-called support function for the isometric immersion. So I think historically this support function is also pioneered by Darboux. So various people studied nonlinear Mogent pair. For example, Changshuo Lin and Nirenberg, Qin Han, Hung Zhu Li, and more recently, Lewis Paxat. So these are the results from the Mogent pair approach. And also, so Nash approached this problem differently. So he did it directly looking at the first order system, df equals to g. So that's just the defining equation. And his method, or at least in certain expositions to that, for example, Richard Hamilton's exposition is actually more a flow type, or ODE philosophically approach. And also in the case that if we have a negative Gauss curvature, then we can formulate the problem as a first order hyperbolic system. So Qin Han, Wen Tao Cao, and also Efimov, Tikhonov, the Russian school, and they studied that from this aspect. And I also mentioned a earlier work, a recent work in 2016, I think, by Guiqiang Chen and Cleland, Slamrod, Zhehua Wang, and Ding Yang. So much earlier, there's another thread of work using the exterior differential system. So I think the Gauss and Codazzi equations, they correspond to the first and second prolongation of the exterior differential system. So this has been studied in a long paper in 1980s by Bryant, Griffith, and Young, and also some recent works by Cleland. So etc. etc. This list of methods is by no means exhaustive, but I just want to provide certain ideas for the approaches So today I want to discuss three more and perhaps less known approaches, so which have a similar flavor that actually connect the isometric immersions problem to other problems in geometric analysis, and those problems that actually have certain backgrounds in physics. So the three approaches I want to mention are, so one, the Uhlenbeck's theorem on Coulomb gauge, and its relation with the Cartan's second structural equation. And the second one is pioneered by François Labourie. So he studied isometric immersions by looking from the theory of pseudo-holomorphic curves. So I think Labourie is a student of Gromov. So he found some very striking connections between these two fields. So thirdly, we mentioned some recent works on the fluid dynamical formulations. And of course, many more approaches are yet to be explored. So let's first talk about the Uhlenbeck gauge and the Pfaff system. So the papers are related ones. So one is the recent work in 2020 by Lissinger, and I have a recent preprint. So addressing the arbitrary dimension and codimension case. So let's mention the background of this thread of work. So the work is concerned with the analysis of the Gauss-Codazzi-Ricci equations. So these are the necessary conditions or the compatibility equations formulated in terms of curvatures for the existence of isometric immersions. So for this part, I consider the isometric immersion of an little n dimensional manifold sigma into Rn for capital N. So I consider the ambient space to be Euclidean. So the equations are as follows. So the first one is the Gauss equation. So it says that certain certain quadratic nonlinear expressions of the second fundamental form, so 2 is the second fundamental form, give rise to the Riemann curvature of G, so which is given because in this problem we prescribe the intrinsic geometry. G is given, so R is given. And the second equation is the Codazzi or Codazzi-Mainardi equation. So it says that the gradient of 2, so bar is the Levi-Civita connection on Rn, on the ambient manifold. So gradient bar of 2 is antisymmetric in its first two coordinates. So in some sense, this is a linear equation. And thirdly, this is the Ricci equation. So it says that the Ricci curvature on the normal bundle of the isometric immersion can be expressed as a quadratic expression in terms of S. So S is the shape operator or the Weingarten operator. So it's just a equivalent formulation for 2. So roughly speaking, these Gauss and Ricci equations, they are nonlinear with the quadratic nonlinearity in the second fundamental form. And the Codazzi equation is linear, which takes one derivative in the second fundamental form. And for this problem, we prescribe G and equivalently, we prescribe the intrinsic geometry, and we are solving for 2. We're solving for the second fundamental form. So we're solving for the extrinsic geometry. So a very natural question to ask is whether the Gauss-Codazzi-Ricci equations is also sufficient for the existence of isometric immersions. Well, the answer in general is yes, but of course are subject to various regularity properties. So for example, if you look for smooth solutions, C infinity or C1 actually, so by the early results by Bonnet, the so-called fundamental theorem of surface, and in 1971, Tenenblatt generalized that to arbitrary dimension codimensions using purely differential geometric arguments. So yeah, I think this is the first paper by Tenenblatt. So the answer is affirmative in the case that the second fundamental form is smooth. So this is proved by looking at the classical Frobenius theorem. So yeah, basically we can solve for the connection one form by integrating, and we can verify the involutivity or complete integrability conditions directly from the setup. So yeah, by classical Frobenius arguments, we can get the fundamental theorem of surface or fundamental theorem of submanifolds. And also, if we relax the condition that the second fundamental form is L infinity, or later on to LP, where P is greater than the dimension of the domain manifold. So these they're done by Madari, Saleh, and Zopos. So the answer is also yes. So yeah, roughly what they need is the is the metric G to be in W1P for P greater than N. And then by Mori embedding, everything will work nicely. And in the recent paper by Liesinger, he actually got to this sharp, the critical exponent L2 in the case that we're embedding two surfaces into R3. Yeah, so if we look at the Gauss and Ricci equation, and because we want to multiply two second fundamental forms, so this is the optimal, or 2 in L2. So this is the weakest possible assumption such that these Gauss-Cardazzi-Ricci equations make sense distributionally. Yes. So yeah, as we claimed, I want to talk about, or I want to generalize these Liesinger's result to arbitrary dimensions and codimensions. So this idea is based on two observations. So first of all, the critical exponent, the P in the above page, I realized that maybe independent of dimension and codimension. So the motivation came from this paper by Guiqiang Chen, Marshall Slamrod, and Dehua Wang in 2010. And me with my supervisor Guiqiang Chen also had certain generalizations to say arbitrary manifolds and also pseudo manifolds. So yeah, this Chen Slamrod Wang paper proved the weak continuity of the Gauss-Cardazzi-Ricci equations in LP for P greater than 2. And the important thing is that this 2 is critical regardless of dimension and codimension. So it made me think that probably this little n and capital N, they're immaterial. And also, if we look at the Gauss-Cardazzi-Ricci equations, so using the exterior differential forms by Henri Cardan, that can actually be summarized as the second structural equation. So in shorthand, this is d omega plus omega wedge omega equals to 0. So this capital omega here is the connection one form on the tangent bundle, and is defined by basically is by putting the Levi-Civita connection on the on T sigma and on the normal bundle together, and with the off-diagonal entries being the second fundamental form. And this omega is a one form taking value in the anti-symmetric matrices. Okay, so in this recent preprint, we proved the following. So I apologize for these complicated looking formulation, but actually the idea is rather straightforward. So let sigma G be an n-dimensional simply connected closed Riemannian manifold, so it's compact without boundary, with metric in W12. And of course, to make sense, I also need G to be L infinity. So I let E be an arbitrary vector bundle. So in the end, I want to identify this vector bundle with the normal bundle. So I let E be a vector bundle of rank K over sigma. and equip E with a, again, W12 cap L infinity bundle metric and a compatible L2 connection. So suppose I also have a tensor field S, so which satisfies this symmetry condition. So this is S is just the putative shape operator. And I can also define the second fundamental form, which is equivalent to S by a different contraction. So that's it. So if I have these data, and then the following are equivalent. So the first one is the existence of W22 isometric immersions. And as we remarked, for this isometric immersion, I can also identify the normal bundle, the connection on the normal bundle, and the second fundamental form with E, nabla E, and 2 respectively. So everything behaves naturally. And so the existence of W22 isometric immersions is equivalent to the Cardan formalism. So d omega plus omega wedge omega equals to 0. And this is also equivalent to the Gauss-Codazzi-Ricci equations. Well, of course, we want to talk about the PDEs in the weak sense or in the distributional sense. And as remarked, this L2 is optimal for these equations to be defined distributionally. And also, in this case, this iota isometric immersion, whose existence is shown, is unique up to Euclidean rigid motions. So here, of course, there are other technicalities. So we have to throw away some Lebesgue null sets. So to do that, let me sketch the proof. So first of all, the equivalence between the Gauss-Codazzi and Ricci equations and the second structural equation, this one, is classical. So it follows from a direct computation. And of course, also, their weak formulations, they agree. And now let's assume for the moment that everything is infinity. And what we can do, so by the result of Uhlenbeck, we know that there exists a Coulomb gauge P, which is W12. So it's in W12, and it takes values in the special orthogonal matrix, special orthogonal group, such that divergence of theta is 0, where theta is P inverse grad P plus P inverse omega P. And then, a tedious computation, but it's purely algebraic, and also, it uses the structural equation, will show that actually this theta satisfies the same structural equation. But what's more, we know that the theta is actually divergence-free. So by a simple Hodge decomposition argument, we can actually prove that in this case, we can have theta to be 0. So of course, we need to equip that with the correct boundary conditions and initial data, but this can be done. So if I have that, then P inverse grad P plus P inverse omega P equals to 0. So since P is invertible, so grad P equals to minus omega P. And this is the Pfaff, the so-called Pfaff system. So the Pfaff system is actually the crucial ingredient in the existence result shown by Tannenblatt, using only the Frobenius theorem. So we can replace this Pfaff result for the Frobenius result. So in this case, we can get the existence. So I'm sketching the proof that if Gauss-Codazzi-Ricci equation is satisfied, or if the structural equation is satisfied, and then there exists a W22 isometric immersion. And of course, I start with this domain manifold to be simply connected, and then by a monodromy argument, I can show I can have the global to local to global result. So I can prove that globally, and also the uniqueness follows by the uniqueness up to the ambient ambient Euclidean motion that can be proved also by playing with the Coulomb gauge. So now the problem is what if this connection one form is only in L2? Well, here we have various places that we have to smooth out things. So the first non-trivial thing is there's a nonlinear smoothing scheme due to Sorin-Madari. So Madari discussed the structural equation and yeah, whether we can smooth that. Well, the structural equation is nonlinear, but the nonlinearity takes a nice form. So also by a Hodge decomposition argument, if you play with the divergence part and the curl part separately, we can actually get a smoothing for this nonlinear equation. So this is by Madari's trick. And next, so in this way, I start with omega epsilon, the smooth versions for omega, and it converges to omega in L2. So I want to show that for each omega epsilon, I can find a Coulomb gauge P epsilon, which also converges to omega. So here, I found this nice paper by Armin in 2010. So yeah, he discussed a variational formulation for the Coulomb gauge. And yeah, I think Armin's paper only works in L2. So yeah, that's what really helped me here. So by using that variational formulation, we can prove an L2 stability result for the minimizer, or for this Coulomb gauge as a minimizer. And this will help me to show the convergence for the Coulomb gauge. And yeah, except for these two, the other smoothing arguments are sort of more straightforward. Yes, so this is the first part of my talk. So about the Uhlenbeck gauge and the Pfaff system. So next, I'll move on to a different direction. So this is for J holomorphic curves or pseudo-holomorphic curves. So yeah, as we mentioned, this work was pioneered by François Labourie, a student of Gromov. So in 1989, he wrote a French paper in GDG, which reformulated the isometric immersion problem. So yeah, here by elliptic, he means the Gauss curvature greater than 0. So yeah, he relates that problem to a pseudo-holomorphic curve for the one jet. So yeah, I'll discuss more later. And also in a recent preprint, we showed that Labourie's result actually give us some general solutions for the Weyl problem, but with fewer regularity assumptions. Okay, so the setup is more general than the classical Weyl problem. So here, let sigma g, the domain manifold, again be a topological S2. But yeah, here we only assume that the Gauss curvature is strictly greater than some real number k0. So this can be very negative. And the ambient manifold n g bar, so that's three-dimensional, and yeah, we assume that to be simply connected. So here we only need the sectional curvature to be strictly less than k0. So this n3 doesn't have to be of constant sectional curvature. It doesn't have to be a space form, but there are some like strict inequalities for the curvatures here. So if there is an isometric immersion and such that okay, the difference between the two curvatures is greater than epsilon, greater than or equal to epsilon, which is strictly positive, and then so in Labourie's paper F is called epsilon elliptic. So of course, if n3 g bar is just the Euclidean 3 space, and this k square is precisely the Gauss curvature of my sigma of the topological S2. So in the general case, this k square is called the sigma 2 curvature or the extrinsic scalar curvature. So yeah, for example, in this nice paper by Pengfei Guan and Suyan Lu. So yeah, I want to show the following result. Yeah, so unfortunately, I didn't write this theorem explicitly in the current version of this paper on arXiv, so I'll amend that later. So yeah, using this J-holomorphic formulation, we can actually prove that if G and G bar they're in C3, then up to the above conditions, the strict inequalities compared to K naught. Okay, so there exists an elliptic isometric immersion F. So what's the point? Well, in 1960s, Heinz and Pogorelov they proved this C3 result, but only for N being a space form. So later on, actually, Fenghua Lin has a different proof, a very nice one, yeah, through only the certain harmonic map arguments. So yeah, Heinz and Pogorelov's results are dealing with the ambient space forms, but here we don't have to require the ambient metric to be of constant curvature. Yeah, so the important thing is the very ingenious setup of Labourie. So if we start with an epsilon elliptic isometric immersion, and then let's consider its one jet. So the one jet consists of f of x and df of x. So yeah, consider the Taylor polynomial up to the first order. And that can be viewed as a pseudo-holomorphic or J-holomorphic map from sigma into the fiber bundle, which is consists of all the linear isometries from T of sigma to Tn. Okay, I call this fiber bundle E. So pseudo-holomorphic, yeah, as we know, or yeah, as we the PDE people, we understand it. So it's a generalization of the Cauchy-Riemann equation, so which is of the first order and which is elliptic. So there's a regularity theory for that. And by definition, so a map is pseudo-holomorphic if D, or the exterior derivative of that map, intertwines with the with the two almost complex structures. So the tangent space of my E bundle splits into two parts. So the important component, I call it V, consists of the map sending two vectors, U and V, to a three vector, so to U, sigma U, U, Cu, and K times Cv. So this sigma is a that actually captures the almost complex structure for V. So if I send UV to V minus U under this sigma map, and you can check this J is an almost complex structure. And for an isometric immersion, we can take this C, the point at which I'm taking the tangent space to be df, to be the exterior derivative. And then I consider the image of my one jet. So the image of the one jet maps into this component V for my bundle E, and also being epsilon elliptic means that J1F sigma actually maps into the part that the extrinsic scalar curvature K is strictly positive. And what's more, so yeah, all of these are discussed in Labourie's paper. Okay, so what's more, this V component is calibrated. So in the following sense, so yeah, this notion calibration is taken from the calibrated geometries by Rhys-Harvey and Blind-Lawson. So it's calibrated in the sense that there exists the one form defined on some neighborhood of the one jet, such that this D of phi acting on X and JX is strictly positive. Okay, so yeah, once we have the boundedness and the calibration, it follows from Gromov's Schwarz lemma that J1F is actually precompact, and also J1F is smooth, and it has uniformly bounded derivatives of all orders. So the compactness of V is understood with respect to the Hermitian metric U on this component, bundle component V. So this mu is as follows. So yeah, basically it is just G, but weighted by square root of the sigma 2. Okay, so given these J-holomorphic formulation, now I can prove the result that if I have three C3 metrics and then there exists an elliptic isometric immersion. Yeah, so yeah, the thing is by Labourie, actually he found a first order PDE for the mean curvature. So this is sort of equivalent to the Gauss-Codazzi equations, or Gauss-Codazzi equations imply this equation. So this equation takes the form of dH composed with J. So J is the almost complex structure on sigma and 2. So here I assume the curvature conditions. So yeah, in particular, the second fundamental form is a positive definite. So I can view that as a metric on sigma. So actually, yeah, both in Labourie's work and in Fanghua Lin's work, I think the crucial thing is to look at a map from sigma 1, from the first fundamental form to the second fundamental form. Okay, so if J is the corresponding almost complex structure, then DH composed with J equals to H times beta. So beta is a one form which is globally defined on this big bundle E. So you can treat it as universal. So that plus some the pullback of the connection one form times H square minus 4K square. So actually, if we divide both sides by H square, and then I can reformulate this equation as follows. So yeah, so we can reformulate that equation as an equation for W, where W equals to 1 over H. Yeah, so if we look at this equation, it's a first order PDE. So on the left-hand side, we have dW composed with J. And on the right-hand side, we have a first order term in W and a quadratic term in W. And also by the Leland-du-Schwartz a la Gromov, to show the existence of isometric immersions, we only need to prove that W is strictly bounded away from 0. Because that implies that H, or the extrinsic geometry, is uniformly bounded, and that together with the calibration we discussed before satisfies the assumptions for Gromov's Schwartz lemma. So to prove that, we notice that if we take another derivative and then we get Laplacian, so thanks to the presence of this J. So then we can get a second order elliptic scalar PDE for W. And also by the ellipticity condition, we are looking at the positive solutions. And also in the degenerate case, we can look at the non-negative solutions where W equals to 1 over the mean curvature. So if I do the usual Harnack estimate, so actually this equation by taking another derivative satisfies the structural assumptions to apply the classical Harnack results, say by Schrödinger. And we can actually prove that W is uniformly bounded from below. And if I do a smoothing and the usual limiting argument, I can prove the existence for G and G bar. And the important thing is that C0, I can take it, well, by the direct arguments from estimates from Harnack, I can take it to be only dependent on one derivative of K. So that amounts to the C3 norms of G and G bar. So the original motivation of my recent preprint is the following. So using a similar Harnack argument, we gave a sufficient condition for the existence of degenerate elliptic isometric immersions. So this is more in the spirit of Pengfei Guan, Yan Li. So, and my condition is in terms of the degeneracy and blow-up rate of the smoothing families of the two principal curvatures. So roughly speaking, if these Okay, so if I have a smooth approximation family of the metrics, and if the smaller principal curvature degenerates to 0, and at a rate too much faster than the blow up rate for the second for the larger principal curvature, and then we should get and then we should we should get the existence. So finally, I'll briefly talk about some recent fluid mechanical formulations. So this includes the works done by my supervisor Guiqiang Chen and Marshall Slamrod and Zhehua Wang. So in this nice paper in 2010, and one of my recent works this year. Okay, so in this case, I'll focus on the isometric immersions for negatively curved surfaces into Euclidean 3 space. So for the negative curvature, this problem is hyperbolic. So once we view these two space variables x and y as x and t on this on the domain manifold. So in fact, we can show that the curvature strictly negative is the same as the strict hyperbolicity in the conservation law community. So for the Gauss-Codazzi equations, we are solving for the second fundamental form. So this second fundamental form is a 2x2 symmetric matrix, so it has 3 components. And we can eliminate one of the components using the Gauss equation. And then the other 2 components, they satisfy the 2 Codazzi equations. And by viewing this second spatial variable as t, we can view it as a hyperbolic balance law. So it is of the form of a 2D compressible Euler type equation. But for a balance law, so there are like inhomogeneous terms, there are source terms, and these source terms, they involve the metric components and also gamma ijk, also the Christoffel symbols. And then, starting from the Chen-Slamrod-Wang paper, they used the method of invariant regions in the study of hyperbolic PDEs. So the idea is if the initial data lie in some regions in the phase space, so such that on the boundary curves, the source terms, they have favorable signs, and then the solution are uniformly bounded in L infinity. So actually in the phase space, the solutions as time evolves will be captured in these invariant regions, in these regions enclosed by these nice boundary curves. So in our case, for the fluid formulation for the Gauss-Codazzi equations, the topological boundary of these invariant regions are given by the 0 loci of the source terms. So in general, these are gamma ijk's weighted cubic curves. So there are algebraic curves in UV of order 3 in general. So the trouble here, of course, is the invariant regions, they do not always exist. So using this method, so in these 10 years, there are various existence results for like new families of negatively curved surfaces C11 isometric into R3. But these existence results are rather sporadic, and of course, they're based on the nice structures for the source terms. To ensure that, usually we can only look at relatively simple forms of the metric. So in this original paper by Chen, Slamrod, and Wang, and also later by Cleopatra Christoforou, they found the existence for several families of generalized catenoids. And in 2015, by Wentao Cao, Feiming Huang, and Zhehua Wang, they found various generalized helicoids. And surprisingly, these 2 families, unless it's reduced to the classical catenoids and helicoids, they're actually not isometrically deformable into R3. So they're in R3. So they are actually very distinct families of objects. And we also found certain generalized endoper surfaces and quadratic surfaces. So yeah, what I'm doing, what we're doing is basically to look at some one parameter family of perturbations of the classical minimal surfaces, because that can ensure the Gauss curvature to be strictly negative. So yeah, again, these existence results are more or less sporadic, and yeah, I think new ideas are really needed to show the existence of the existence results for more negatively curved surfaces. Okay, I'll stop here. Thank you very much.
Thank you very much. So, other questions, remarks, comments? Preferably with a microphone. Gofan?
Yeah, in the second result, so I would like to ask some questions. So your second paper. Hello?
Yes.
In your second paper, so this is how you use the structure. So the important is, at least to me, is so you should have use such kind of structure. So or the calibration, yeah. Will you use this?
Yeah, so the calibration will give us that if we can bound H, if I can have L infinity bound on H, and then it implies the existence of isometric immersion. So I use it there. So it's hidden in this Schwarz lemma.
Oh, okay. So what you did, so at least so it's actually the second order equation for the H, or the inverse of H.
Yes.
Can I understand it? So I'm saying it's right?
Yeah, that's absolutely correct. So
okay.
we just need to get the a priori estimate on H. And
okay.
Because here we have the second order elliptic equation, so we can just do that. So in this formulation, it's nice that the source term only involves 3 derivatives. So that's the observation.
Okay.
Yes.
Thanks.
Thank you.
Any other question, remarks, comments? Let's see if somebody. All right, so let's thank Siran again.
Oh, thank you. Thanks for the invitation.